So today we will start the first topic. It will be about the basic elements in engineering seismology. This is the first of the two-part section of this course, which is about the seismic hazard. So the first part is basic seismology, first you can say chapter, and the second will be the seismic hazard assessment. So several of the concepts, in fact all of the concepts in the seismic hazard analysis, it will be coming from the basic engineering seismology. So first I'll cover some quick concepts in engineering seismology, and then we will go to the seismic hazard analysis, right? So this is the first part in which we will be understanding the nature of earthquakes, because our ultimate goal is that we want to assess the structural performance and improve its performance against future earthquakes. So the first step would obviously be to understand the nature of earthquakes, what is the phenomena itself, what are the hazards associated with that, right? So earthquake have several hazards. The ground shaking is one of them, right? Surface rupture is also an earthquake hazard. Earthquake induced landslides is also earthquake hazard. Liquefaction, tsunami, all of them are earthquake hazards, right? Ground shaking or ground motion is one of them, the primary hazard, right? So when we talk about earthquake hazard in the context of building design, we actually mean ground shaking hazard, right? The effect of ground movement or shaking as a result of earthquakes. But there can be other hazards associated with earthquake also. So let's start a quick introduction about earthquakes. I'll be very quick because I already have a very detailed video playlist on basic seismology and hazard assessment. So in these 2 or 3 sessions with you, I will just have an overview of what are the issues associated with earthquake phenomena, right? So I'll stop only at important places. Some minor details I'll keep on skipping, right? And I assume that if someone wants more information, he or she can check that detailed playlist. So earthquake is a shaking and vibration at the surface of earth resulting from underground movement along a fault plane or from any volcanic activity, right? It is a result of a sudden release of energy in the earth's crust, which release in the form of seismic waves. Those waves travel from the point of start, from where they originate, and they travel outwards away from that point. And that release of energy, we experience them as ground shaking and ground movements. So it is a sudden and sometimes catastrophic movement of a part of Earth's surface. There are several types of earthquakes. Tectonic earthquakes is the most common type, which are the result of interaction between different pieces of lands or plates. So they are produced when the rocks break suddenly in response to various geological forces. I'll give you an idea about what actually caused those forces, which ultimately store energy and then release in the form of earthquakes. There are volcanic earthquakes also. As the name indicates, they are associated with the volcanic activity. So volcanism is also a geological phenomena which is closely related to earthquakes, right? So you can say that the plate tectonic theory, which actually explains several of the causes or issues related to earthquakes, also covers this volcanism. So I'll show you what this phenomena actually is and why it can also cause an earthquake. There can be collapse earthquakes because underground there can be cavities which can just settle down. There can be you can say hollow areas or rooms in different mines or certain structure of land which can just settle. They can also be caused by massive landsliding. Sometimes a sudden movement of one piece of land can also cause an earthquake that we can categorize under these collapse earthquakes. Human cause explosion earthquakes. So it is obvious that several of the human activity, for example, explosion from chemical or nuclear devices, can also cause ground shakings, which can be categorized under these kinds of earthquakes. But most important is this one. So when I say earthquake, I mean actually tectonic earthquake, right? So about the causes of earthquake, obviously I'll skip several of the minor details. I assume that you will go through the detailed playlist. So several of the ancient mythologies and folklores, they have different opinions about what actually causes earthquake, right? So this is one of the you can say folklore from Japanese mythology. It is conventionally said that there is a giant catfish which lives under the earth, and whenever it moves, we experience that movement in the form of earthquake, right? So this is an ancient story coming from the Japanese mythology. Different other cultures also have the same similar stories about the causes of earthquake, because this is a natural phenomena which is being experienced by ancient human civilizations also, prior to the development of all those scientific theories and procedures, right? So different cultures have answered this question differently. What causes these earthquakes? But we now know with more confidence from the developments in last 100 years, what actually is the phenomena which results in the earthquakes. The very first development which we can have in this series of developments is 1891, Professor B. Koto, Japanese seismologist. He was the first one to identify correctly that the sudden failures or deformations on the surface of earth, which you can see after an earthquake sometimes, they are not the result of an earthquake, actually they are the cause of the earthquakes, right? So now we know that earthquakes are the result of sudden movements of different pieces of lands. Sometimes that movement manifests on the surface also. It can be seen or visible from the surface also in the form of deformations. After an earthquake, you may identify that there can be two pieces of land which just slide past each other, or one piece of land just come above the other one, or they just go away from each other. So these deformations or movements which are visible from the surface, they are actually the cause of earthquake and not the result of earthquake. So this realization was the very first step toward rightly identifying the reasons of earthquake, right? Prior to that, it was generally assumed that these deformations are the result of earthquake, right? So this was the start of common acceptance that the fractures and faults are the actual mechanism of the earthquake and not its results. So people start believing that there are several fractures or faults which are already there on the surface, under the surface, and the movement occur along them. So they are the one which cause earthquake actually. So those fractures are not caused by that movement. Movement is actually is being caused by these lines or these fractures which are already there, right? So now we know that these fractures or faults on the earth's crust, actually the topmost layer of earth, they are of several types. For example, you can see here that this line, it appeared after this earthquake in Turkey 1999. This one you can see that this was a fence, this was that fence, they were in the straight line, but after an earthquake there is a relative distance between them, maybe around 2 meters or 2.5 meters. So the two pieces of land, they slide past each other, they move relative to each other. Their movement can be sometimes towards each other, or they slide past, or maybe one goes above the other. There can be of several types, right? You can see some other examples of surface deformations after earthquake, right? So you can see one part lifted up from the other one, this one, right? So the second development which you can count in these series of developments was 1906 San Francisco earthquake. An American geologist, Harry Fielding Reid, he investigated the aftermath of those earthquakes and he proposed a theory. And the theory was that strain had been building up over a long period of time and suddenly released in that earthquake. So he said that we can see clearly around 6 meters of the relative displacements between 2 points on Earth, which was not there before. So one possible cause can be that there was some force which was applying on this land, piece of land. There was an already existed fault line or crack at that location, and the strain was being stored in that crack, right? And one day suddenly the stored energy was more than the capacity of storing for that fault, and there was a relative movement between them. There was a sudden slip along that fault line, right? So the two pieces of land, they keep on resisting the movement up till a certain time, but then the stored energy was more than their capacity. They slipped and get to a new position now, right? And that new position have a relative displacement of more than 6 meters roughly, right? So he was not able to explain what causes that movement, what causes that built up of strain energy, right? Or what causes actually for those cracks to exist in the first place. But this was his idea for explaining what have actually occurred in that San Francisco earthquake, right? So later on this theory was you can say validated, and his idea was correct, right? So this is all that detail, so please allow me to skip the details, so I'll just stop at important places, right? So he proposed that elastic rebound theory. He said that just like any material which have already an elastic capacity, and if you apply some energy which is more than that capacity, it will displace to a new equilibrium position, right? So that release of energy, when it is more than the capacity, it releases, right? And that release of energy is what we experience as earthquakes. Partially that energy is converted into heat. So when the slip occurred between two pieces of land, some part of that stored energy converts into heat energy. Some may be into sound energy or some other part, but bigger part converts into some elastic waves which just travel away from that rupture place, right? Those waves, when we experience on the surface, they are experienced as earthquakes, right? This was his idea with no empirical evidence, 1906, right? So this is actually one graphical representation of his idea. The two pieces of land are there, the crack or fault is already there, right? And there is some force which is causing a relative movement. Up till a certain time it will keep on resisting, but when that force exceeds the capacity, it will slip, it will have a sudden slip, and it will come to an equilibrium position at a new location, which can be 6 meters, 10 meters, 8 meters. So there was data available for different earthquakes from the field observations, that how much slip have actually manifested on the surface. But now we know with more confidence that there are different types of these cracks, right? We call them faults. It is a fracture along which the block of crust on either side have moved relative to one another, parallel to the fracture. Normal fault, you can see here that this inclined plane is actually the fault plane. So it's not necessary that the fault line or the fracture is vertical directly, just like in this case, right? It can be inclined also. So whenever there is a inclined crack in the crust, you can either have a normal fault or you can have a thrust or reverse fault. In normal fault, you see the two pieces of land, they are moving away from each other, so one can just slide down from the other. In the thrust fault, as the name indicates, one piece of land just can go above the other, right? In both cases, the movement is along this plane, dotted line, right? So there can be a third type also, strike slip fault, which is vertical crack, right? And this again have further two types. One is right lateral, other is left lateral. If you are standing on one piece of land and other is moving towards your right, it is right lateral, and if the other is moving towards your left, it is left lateral. But in both cases, the crack will be directly vertical, right? So this is that sliding past case, right? So three main types, but there can be kind of combinations of these types also, like it can be strike slip but at a certain angle, or it can be some other oblique slip, for example, right? So this is their detail, but sometimes a real fault can be a combination of these ideal three types, right? So there is a dip angle. Dip angle is the angle which is associated with the normal or thrust faults, that angle from which you define the fault plane actually. So now we know that this sudden release of energy start from one specific point. It doesn't start from all along the existing crack. It starts from a specific point under the Earth's surface, and that point is called focus, right? So up till that time, 1906, it was not known exactly what causes that relative movement, but it was well understood that these two pieces of land which already have a crack in them, the relative movement is being stuck by the relative friction between these two blocks, right? So there is a friction between the two blocks of land which keeps on resisting the relative movement until one day suddenly the energy is released and they slip 5-10 meters, for example, right? So but that slip actually doesn't start all along the length, it starts from a specific point, right? Because that resistance coming from the friction, resistance of that movement, it will be actually located, its resultant will be located at a certain point, right? And then when the applied force is increased from that capacity, we have that relative slip. So focus is the point from which the rupture actually initiate, but then it travels, right? It travels along the fault plane. So the crack is already existing, but the relative movement starts from a certain point on that crack under the surface, right? So can you make a picture in your minds that earthquake originate from a point, right? So the movement actually have a starting point which we call focus, and then that movement travels along the fault plane. Sometimes it travels all along the fault plane, sometimes only the part of that fault line have that movement, right? So when that rupture initiate from focus, the seismic waves or elastic waves, which are actually, you can imagine them as disturbances in the Earth's crust. So that wave is not something physical, it is a disturbance in the Earth's crust. That disturbance actually travel away from that point. The very first point it reach on the surface is directly above that point, right? Because that is the closest point on the surface from that focus point. So that point is called epicenter on the surface, from which you experience the seismic waves for the very first time. And then when they reach to surface, they also travel on the surface, right? So seismic waves are primarily of two types. The one which directly moves in the body of Earth, they are called body waves. So if I am standing somewhere here, right? So the disturbance caused here the rupture, the disturbance actually can reach to me in two ways. One is directly coming from the body of earth, right, from within earth, and one is that it first reached to surface and then from surface it reached to me, right. So there are two basic categories of seismic waves: body waves, which come directly from the point of initiation to you from the body of the earth, and the surface waves, which first reach to surface and then they travel on the surface, reach to you. Obviously body waves are faster, surface waves are slower. Surface waves will be modified by all the geometry or geology which is on the surface, right. So if there is a lake or a forest or some mountain on the surface and that wave travel through that geological feature, that wave will have that signature in it, that it passed from all those things. But body wave directly will reach to you from the focus to your recording station or to your point where you are experiencing, or in case of structural design, to your site, right. Actually I have a slide for that later, but P and S waves are two types of body waves. So body waves again have two types: P waves, primary waves, and S, secondary waves, right. So they are primary waves are longitudinal waves, and S or shear waves or secondary waves are transverse waves, right. So their mode of moving a particular medium particle is different, right. P wave is a push pull like sound waves, right. So it's a shock of that rupture which reaches first to you, and after that is the S wave, which is actually the transverse movement, right. So for structures mostly S waves is more dangerous, right. P wave reaches first because it have more velocity. So just like an explosion, first you experience its shock, right, and then you experience any of its other destructions, right. So body waves again have two types, P and S, and from them P is faster than S, right. So P reaches to your site first, and after a few seconds S will reach, right. And since P is a shock wave coming from the body of earth, so if the earthquake is very deep and you are very close to epicenter, then you may experience a sudden push in the upward direction when P reaches to your site, right. So it depends on how far you are from the epicenter. The difference between P and S arrival will be different. So if I have an earthquake like 200, 300 away, I may have maybe a difference of 10 or 15 seconds between the arrival of P and S. So there are several early warning systems which are based on this idea that they detect P and generate an alarm so that you have few seconds to skip under any safe you can say shelter or something, right. So if you are very close to epicenter or actually hypocenter or focus, right, then the difference between P and S will not be significant. So in that case you may not have much warning from this difference, right. The difference between P and S is a very important parameter which can help us in identifying that how far you are from the source of earthquake, right. So as I have said that if you are 200 or 300 kilometers away from epicenter, then you may have like 10, 15, 20 seconds of the difference between P arrival and S arrival, right. So that difference 20 second, 10 second, 5 second is directly convertible into how many kilometers you are away from the epicenter, right. So if you have that difference at 3 different locations for the same earthquake, then you can identify from where exactly that earthquake generated. So that's how actually we identify the epicenter, right. Within maybe few minutes of an earthquake, you have seen in the media and news that they actually can tell the epicenter, right. S waves or surface waves, they reach to you or your site after body waves, right? So they are the last to reach, but they have different characteristics because they pass from all the geological features, right, and then reach to you. So their frequency is now modified based on what geology was in between you and the epicenter, right? So they have a different frequency content, and their effect on structures is also different, right? They again have two types, Rayleigh waves and love waves, right? So depending upon how they actually move the medium of a particular you can say wave, they again have two types, Rayleigh and love. We don't know much about the internal composition of or exact structure of Earth actually, or a particular part of crust or mantle, for example, right? So we assume it all one medium, mostly for simplification purpose, right? So on surface we can exactly quantify the effect of different geological features, but in the internal structure of Earth, mostly we have almost no knowledge about what actually are the mechanical properties of different layers and different information. All we have to, because there are very less empirical studies possible at that mega level, right? So mostly the information is coming from sophisticated infrared equipment and X-ray studies and similar kind of things, right? This is an example of the slip which is mapped for magnitude 7.3 Landers earthquake, very famous earthquake, 1992. So the color here is showing you how much slip that particular part or that particular point have experienced during this earthquake. So this green part is the surface, and this rectangle is actually showing you the depth. So now you imagine a picture that it is a slip, but that slip is not continuous slip or a constant number of slip along the whole fault line, right? So the red color means around maybe 7 or 6 or 8 meters, for example, and green means 5 meter, blue means maybe 2 or 3 meter or 1 meter maybe, depending upon the shade of blue. So now based on that legend, make a picture in your mind that how that slip actually occurred. It is not one continuous slip. If all the points along the depth of the crust or that piece of land, they slip together like a rigid body, it would have been all one color, right? But it's not like that. Some points have experienced a slip along the depth more than like 5 or 6 meters. Some may be 4 meters, some may be 2 or 3 meter, right? So we don't know much about the internal structure of that crack, from where is the source of that friction coming, where it is jagged with the other part, right? So some part slip more, some less. Sometimes the slip on the surface is almost zero. All those dark blue colors, they are zero slip. But sometimes at that particular surface point here, you have seen maybe a slip of 6 or 7 meters. So after that particular earthquake, if you go to that particular site, you will experience that surface deformation, right? So in most of the earthquakes, this deformation or this slip which occur in the earthquake, it doesn't manifest it on the surface, but sometimes it manifests, right? So along this whole slip line, there can be several places where the slip is even visible from the surface, where the crack or movement have an effect visible on the surface also, right? But sometimes it is not visible on the surface, right? So it means that it is an irregular process, a heterogeneous process. It's not very regular smooth slip between two pieces of land. It is a very complex process because we don't know much about the internal structure or geometry of that crack Imagine a crack in a brittle material like concrete. Can you exactly map it? Because it is very deep, it is difficult to exactly understand its irregular shape or geometry and what will be the source of exact friction at different locations of that crack if I apply two opposite forces on two pieces of that material, for example. So sometimes, as I have said, it is visible from the surface, sometimes it is not visible. Sometimes that crack, even without an earthquake, is visible from the surface, like San Andreas Fault. Some faults are directly, you can identify them from the surface that this is a fault line, but most of them you cannot identify from the surface. They exist, but from the surface you cannot tell that this is a fault line, right? This is another example from the Sumatra Andaman earthquake, which caused that great tsunami in 2004-5. So this is the slip actually, which is mapped with different colors, and you can see a timer here. This star symbol is showing the epicenter, right? And this is a point under which the slip originated or started actually. But after it started, it moved in an arc direction because there was a plate boundary or a fault in that arc direction, right? So imagine that this whole two pieces of land on this side and on this side, they didn't move like together. The slip originated at one point along that crack and it traveled along that crack, right? So sometimes the slip can travel all along the fault line, sometimes it can travel only up till one part of the fault line, right? It depends on all internal geometry and structure and that mechanical properties involved in that process. And we have, as I have said, not much information about all those phenomena here. So you can see red color, it originated from that star point, but then it traveled like here. Around 1200 kilometers of rupture length was actually experienced in that earthquake. So you see here that epicenter is somewhere here, which I am encircling now, and the rupture started from that epicenter, actually below that epicenter from the hypocenter or focus, and it traveled along this path because there was a existing crack or plate boundary or fault in that whole path, right? So if you are located somewhere here, for example here, you are very close to epicenter, but you are lucky because the rupture haven't propagated towards you, right? So it means that the people which are here, these islands, for example, these ones, they will experience far more shaking compared to the people here, right? Because although they are very far from the epicenter, but they are very close to the fault line or actually the rupture. So the rupture unfortunately propagated towards them. It originated very far from them, but since the fault line is towards them, so the rupture actually propagated towards them, right? So it is sometimes it can be seen that the areas which are very far from the epicenter, they may also experience very high shaking, right? Because they are close to the rupture actually, although away from epicenter. So let me skip all these figures. You can find very good illustrative figures for different types of fault. So you can see here thrust fault, one piece of land is above the other. There is another very famous San Andreas Fault which is directly visible from the surface. So you can exactly identify that this is a crack in the crust which is going down. This figure is from 1995 Kobe earthquake in Japan, very famous earthquake, and there was a lot of earthquake research after this earthquake, right? So several of the research findings which laid the foundation of modern earthquake engineering, they can be rooted back to this earthquake, right? 1995 Kobe earthquake. So this is a figure taken from one article, and what is actually shown here is that this shaded area is the fault line. The epicenter is somewhere here, right? I will show another figure next, but epicenter is somewhere here. It is not even in this map, and this shaded area is actually the fault line. And wherever they found a dead body, they mark that on GPS. So all these black dots are actually deaths, right? So you can see here directly there is a 1-to-1 correlation between the location of fault line and the destruction, right? So deaths is just one of the damage, but all the economical loss, other social losses, all the destruction of buildings, bridges, everything, it was all located along this whole fault line and not towards the epicenter only, right? So you can see all this shaded area have many dots. As you go away from that shaded area, there are less dots here. Similarly, earthquakes can also trigger fires, right? There are earthquake induced fires. There can be industrial structures or nuclear power plants, nuclear facilities, which if they are shaken, they can trigger fires, right? So all these fire symbols are the locations where this Kobe earthquake triggered fire, and they are also lying on the fault line, right? So this is the fault line actually like this, and this is the epicenter, right? So sometimes it is also very important how far you are away from an existing crack or fault line, right? So sometimes distance from epicenter may not be that important. This is another example from the same Kobe earthquake. So the red dots now shows aftershocks. So once one major earthquake occur, the earthquake's crust sometimes it is still not stable, and there can be certain subsequent slips or ruptures. Those ruptures cause aftershocks, right? And there can be foreshocks also, that before a major slip there can be certain small ruptures or small slips. They are called foreshocks. So sometimes an earthquake occur, and after some time another bigger earthquake occur. So then we say that this is the main shock and the previous one was the foreshock, right? And there are series of several smaller earthquakes after a major earthquake until the earth's crust is completely stable, and all the points on the surface they achieve a new equilibrium stage. And all those minor earthquakes, they are called aftershocks. They are actually mostly dependent on the magnitude of the main shock. If the main shock is magnitude 8 or above, then there can be several of the aftershocks. They can span over many days, right? So if the main shock is a bigger earthquake, large magnitude earthquake, there can be more aftershocks for such an earthquake. At geological level, you can say that it depends on the internal structure and the process or phenomena associated with accumulation of strains and then subsequent release, right? So you may have a situation at a certain site or close to a certain site where the strain energy is accumulating and releasing frequently. The capacity for holding that strain for that particular crack is less, so it stores for maybe 50 years and then release. And there can be a situation where the strain can be accumulated for 3000 years and then release once, right? So it all depends on the nature of those seismic sources or these cracks, nature of these cracks, right? So the phenomena is so grand scale level that within our lifespan or within the next few generations of lifespan, this trend is not going to change, right? The phenomena is associated with thousands of years. So if and this is the basis for the seismic hazard assessment, that we take the data from past 100 or 200 years and then we project it for future. Why we can do it is because this phenomena is not going to change in next 100 or 200 years. The same trend is going to be followed or you can say the same phenomena is going to continue, right? So actually the process of hazard assessment is an attempt to understand the nature of those seismic sources. What is their recurrence rate, right? How frequently they produce earthquake in past, from the past data, right? And then we project that same trend in future also to forecast the future hazard, right? So we understand based on past data, and then we perform the statistical analysis and project it for future in probabilistic framework. After a certain earthquake, we can also have readings at different locations of PGA at that for that particular earthquake, and we can also draw a map after an earthquake of PGA values which were experienced during that earthquake. These kind of maps are called intensity maps, because they tell us that what was the intensity of that earthquake in past, right? So whenever you see a PGA map, it is not necessary that it is a hazard map for future. It can be showing the values experienced in some past earthquake, right? So please do not confuse between the intensity map of any past earthquake and the hazard map, which is showing the expected PGA values for future earthquake, right? So these black dots are actually the recorded accelerations under that Kobe earthquake, right? So you can also make a map of PGA from, if you have enough readings from one particular earthquake, right? So this earthquake was recorded at several locations along the whole Japan, and then the red dots here are the aftershocks, and those aftershocks are all located in the same fault line, which shows that they are dependent earthquakes, right? The main shock is assumed independent, but all the foreshocks and aftershocks, they are called the dependent earthquakes, because they are the result of one big slip, right? The one big slip triggered those earthquakes actually, right? Earthquakes also occur on moon. They are called moonquakes. So actually these black dots are the recorded acceleration values. General trend is that as you go away from a particular seismic source, and now when I say source, I don't mean epicenter only. Now you can understand that I mean the whole fault line, right? As I go away from that, the general trend is that the recorded PGA values from one particular earthquake should reduce, right? But obviously there are certain other factors also which contribute to that trend. In general they reduce, but sometimes you may see that at a particular site closer to that fault line the number is lower, and when you go away the number can be higher also. It all depends on the local soil effect, because the recording station is situated on the surface, or maybe 2 or 3 or 10 meters from the surface, right? So the shaking can be modified by the top soil layer. Your station is resting on that top soil layer. So depending upon the soil type, the earthquake can be modified, the shaking can be modified by that soil, right? So the shaking which is experienced by our structures is the one which is experienced on surface, and not like at the bedrock level, right? So sometimes the situation is that the station is resting on loose soil, sometimes hard rock, sometimes directly on the surface, sometimes 10 meters below the surface. So sometimes the loose soil can amplify ground shaking, and stiff soil can de-amplify also, right? So the local soil effect can modify that general trend. But overall, if you have enough points, you will see that as you go away from the seismic source or fault, the recorded PGA value will reduce, right? And the relationship between these two things is called attenuation model. This is an important component of PSHA, attenuation model, which I explained in maybe first session also, that if I record, because let's say this is the fault line, and all the black dots are the are the PGA values recorded at different distances. So for each point I have the distance from the fault line also, let's call it R, right. So this R is different, this R is different. So I may have hundreds of data points, hundreds of PGA values at different R values, right, source to site distance. Finally, what I can do is that for one particular earthquake, I can plot the R value, source to site distance, and PGA value on the top. The general trend will be like this. If I have many data points, the general trend will be that as I increase R, the PGA is reducing, right. So I can have a best fit line like this. This is called ground motion prediction equation, GMPE, or attenuation model. Attenuation means that how the energy is, the seismic wave is losing its energy with distance, right. So why it is called GMPE? Because it is used to predict the ground shaking for a given distance from the seismic source for other earthquakes. So people or researcher actually gather this data for hundreds of earthquakes, recorded earthquakes, and then develop the equations or models for that. Now with a given model available, what I can simply do is that I say that I am 50 kilometer away from a particular seismic source. So corresponding to 50, I will pick the PGA value, and obviously this line will be different for different magnitudes. So it will not be one line, it will be a family of line. So if I can do is that this exercise that I am 50 kilometer away from a fault which can produce magnitude 7. I can pick the magnitude 7 line, let us say M7 line, 50 kilometer is a distance, this will be my PGA. So I can predict PGA using such a model if I am given with the distance from my fault and the maximum possible magnitude which that fault can produce. Obviously that information will be coming from historical data, past 100, 200, 500 years, we will see that what maximum magnitude that fault have produced, right. This whole exercise is called DSHA, deterministic seismic hazard assessment, that you directly predict using a GMPE and the information about your fault and your distance, you directly predict the hazard parameter which is PGA in this case, right, at your site. So if I am given with a particular fault, its distance and the maximum magnitude which it can produce, I can select a GMPE from literature which is applicable to my seismotectonic environment, and I can do that exercise to predict PGA at my site. If I do this, I am actually doing DSHA, and if I keep on doing it for all possible sites in the whole country, I can develop a map of PGA from DSHA. It will be a hazard map, right. But this DSHA, which is very simple by the way, is no more used, or it is not the only option now for seismic hazard assessment. We also have the PSHA, probabilistic seismic hazard assessment. So let me conclude the discussion about the nature of earthquakes. This is another example, Yogyakarta, Indonesia. Actually the rupture originated from here, but it traveled in this way, following the fault line, right. So the shaded area in red color is all area with significant damage. So even if you are here, you are in significant damage area, although you are very far from the epicenter, right. Indonesia is a country which have a building stock very similar to us. Majority of the buildings, they are of unreinforced masonry bricks, right, same as us. So the rupture zone all have experienced very strong shaking in that particular Yogyakarta earthquake, and then as you go away from that rupture zone, you have a zone of strong shaking, then medium shaking or low shaking, for example. So let's now come to the actual reason why we have this relative slip or movement, right. The very first development in this regard was in 1910, Alfred Wegener We call that theory as the continental drift theory. Most of you might have already have an idea about that. Alfred Wegener said that around 200 million years ago, the earth consisted of all one big piece of land or one continent, which is called Pangaea, and there was only one ocean, one piece of land, one ocean. For some reason which Alfred Wegener at that time couldn't explain, later we came to know the actual reason. He said that for some reason it break apart into different big chunks or pieces of land, and they start moving in different directions with a very small rate of movement, like 1 centimeter per year. It is a rate which you can imagine by you can have an idea that at this rate your hair may grow or your nails may grow very small, which is not directly observable. But if you keep an observation after certain time, you will feel the difference, right? So 1 centimeter per year or 2 centimeter per year, this is the rate of their movement. So for some reason unknown at that time, he said that these pieces start moving in different directions, and this movement is called continental drift. This is actually the starting point of theory of plate tectonics, right? So this is the first observation which led to the development of that detailed theory. So if we reconstruct that movement for millions of years, so at the bottom you see from 150 million year up till 0 million year, which is today, you see how these pieces of land, they break apart and moved in different directions. For example, around 150 million years ago, India was somewhere here, right, at the bottom, and then it traveled and it crashed into the upper piece of land around maybe 50 or 60 million years ago, right. So this is India moving in this direction. Now see India again, moving at the bottom, and it is crashing into the upper piece of land, and it is continuously in a state of that crash from last 50-60 million years, right. It is shoving into the upper piece of land, right. So similarly, you can see the North and South America, for example, the Africa and South America, they were once one, and they break apart and become different pieces of land. So this is how the outer surface or the shell of earth is moving. If you just approximately reconstruct that movement, so around 150 million years is shown here with like 5 seconds, right. So now we know with more confidence that what was the situation of that Pangaea at different times. 150 million years, it was all one. Around 100 million years, this much was the separation, and then maybe 1 million years ago, we have the continents at almost the same location where we can see them today, right. But they are still moving at the same rate, 1 centimeter, 2 centimeter, depending upon different pieces of land per year. I'll skip all that detail, but there are several of the implications of this Wegener's theory which led it to the development of theory of plate tectonics. But let me just directly tell you what is the state of the art now. We now know that Earth's crust or topmost layer is not one continuous piece of land. It is made of several big pieces of land or plates, right. And it has 3 major layers. One is crust, then mantle, and then core, right. And sometimes we use the word tectonic plate for a combination of crust and some upper part of mantle, right. So there is a classification about lithosphere, and then asthenosphere, and then the core. So one simple classification is crust, mantle, core, but then based on geological properties, for example, we call it lithosphere, which means crust as well as some upper part of the mantle also, right. And then below that is asthenosphere, then other layers. So the bottom line is that the topmost layer is not continuous, it have cracks, right. This is the simplest representation of Earth's structure. We have crust, then mantle, then core, outer and inner. On the other side, you have another classification, that sometimes we say that crust and some upper part of the mantle, we combinedly call it as lithosphere, and then below that is the asthenosphere, and then other layers, right. All oceans, continents, mountains, everything is on that crust, right. So crust doesn't mean continent. Continents are on crust. Crust is the outermost layer on which you have oceans and lands, right. So when I say one particular continent is moving, which means actually the whole plate on which that continent is located or situated, that is moving actually. Core is roughly of the size of moon. Okay, the temperature of Earth's core is same as the temperature at the surface of sun, around 6000 degrees centigrade, and a core itself is composed of outer core and inner core. Outer core is liquid, mostly made of molten rocks. Inner core is solid, mostly made of iron and nickel, and this is the reason why we have a magnetic field for Earth, right. Earth also have a magnetic field, which means it is a big magnet, right. It has a north and south pole, and it have a very weak magnetic field. The mantle is mostly molten rocks, right. So it is a big ocean of molten rocks. Just to give you an idea about the scale, because this figure is not to scale. The radius of Earth is 6400 kilometers, right, and crust is from 0 to 100 kilometer, mostly like 50 kilometer average, you can say, right. Places have different thicknesses of crust, but you can say average 40 to 50 kilometers. Now that is very small compared to the overall radius. If you see diameter, what will be 12800 kilometer. Based on that diameter, compared to that diameter, 50 kilometer is nothing, right. So the crust is actually very thin compared to the overall size of Earth, although it is like 50 kilometer, which is very thick according to our you can say intuition or understanding, right. But that 50 kilometer is nothing compared to the overall diameter. So you can imagine that it is the ratio is same as the shell of an apple, for example, right. The outer layer of an apple, it is almost of the same scale. So crust is very thin. So we are literally living on a very fragile layer which is resting on molten rocks, right. Then we have around 2900 kilometer start of the outer core, and then 5100 kilometer from the surface start of the solid inner core, right. So all the oceans or continents, mountain ranges, everything is on crust, right. The average thickness of oceans is 5 kilometer average, right, which is again nothing compared to the overall size. So if we reduce the Earth into a size of a ball, the oceans will simply disappear. It will be a very small, even not even visible layer of moisture on that ball, right, if you make a picture of that big scale. So now come to the reason why we have these plate movements. Currently we know that these plates, which are actually making the Earth's crust, they are moving and they have cracks in between them, and each of the plate or big piece of land is moving in a particular direction from thousands of years. Actually it is moving from millions of years, but its trend is, you can say, almost same from hundreds of years from past history, right? So they are moving in different directions, and sometimes two plates have a movement direction such that they are moving towards each other. Sometimes two plates are moving away from each other, sometimes means at some locations. And at some locations on that globe, two plates are sliding past each other. Their movement is opposite, but they are sliding past. Not towards each other, not away from each other, but sliding past. So there can be three types of these plate movements or plate boundaries, right? And now make a picture in your mind that these plates, which are solid pieces of big lands, they are resting on mantle, which is a liquid ocean of an ocean of liquid rocks, right? And they are kind of floating on them, right? Now if there are any movements or currents in that ocean of liquid rocks, the plates will follow that movement, right? So if there are waves, any waves or currents or movements in that mantle, the topmost layer obviously will follow that movement. Now we know that there is a process called convection, the same process which we observe when we boil water, that when we have a pot in which we have water for boiling, the water which is close to the bottom, close to the fire source, it have a higher temperature compared to top water at top, right? So it moves up, and the relatively cooler water from top goes down, and there is an internal movement which start because of that boiling process, right? This process is called convection, right? And heat actually moves in that medium because of that process. Exactly the same process is happening in Earth's mantle also. Core has a temperature equal to the surface of sun. The molten rocks which are close to the core, they have a relatively higher temperature, these rocks. So the part of mantle which is close to core have a relatively higher temperature compared to those which are close to crust, right? So therefore there is an internal movement happening inside mantle, right? So that whole ocean of magma is moving due to the process of convection, and obviously the plate on top of that magma obviously will follow that movement, right? So depending upon how this convection is happening at different locations, the plate on top is moving in different directions. When we see from top surface, we see plates moving with different rates and in different directions, right? So this is the driving force for the plate movement. The energy is actually coming from, if you trace it back, it is coming from the core itself, right? So the core will stay at this temperature for millions and billions of years. Actually it has been estimated that this whole solar system have a lifespan of around 10 billion years, around which half of the time is passed already. So still there will be billions of years until this core will lose its temperature, right? So which means that this phenomena will keep on continuing. It was continuing from millions of years, and it will continue for the next millions of years, right? So from top, if we see, we can identify different plates. They are moving in different directions, and whenever there are two plates which are meeting, or plate boundary, that boundary can be of three types actually. One is convergence plate boundary, where the two plates movement is such that they are striking towards each other. Divergence, which means moving away from each other. And then transform plate boundary, where they are sliding past, right? So wherever they are converging towards each other, the weaker plate is subducting under stronger plate, right? And if they are relatively stronger, their stiffness is comparable, then they make mountainous ranges, right? So they make Himalayan range, for example, or any other mountainous ranges, right? And if one is clearly weaker than the other, then it will subduct. It will simply go down and sink into the mantle under that stronger plate, right? This process is called subduction. And wherever they are moving away from each other, which is called divergent plate boundary, the magma from the mantle is coming up and making new crust, right. So the crust is actually continuously being created at the divergent plate boundaries, and it is being destroyed at the convergent plate boundaries, right. So it is like, if you make a picture in your mind, it is like Earth is changing its skin continuously. At certain locations it is destroying its skin, and it is being created at divergent plate boundaries. Most of the divergent plate boundaries are under sea, right. So we cannot directly observe the phenomena, and most of the convergent plate boundaries, many of them, they are in land areas, in continents, when they make mountainous ranges or subduction zone, for example. And there can be transform plate boundary, where the two pieces of land are sliding past each other. So in this whole map, all the convergent plate boundaries are shown with this symbol, subduction zone or convergent boundary, the line with small triangles, and the simple line, this one zigzag line, is showing the divergent plate boundary or transform plate boundary, right. So we now know that we have a very big Pacific plate, South African plate, Nazca plate, Caribbean, then Indo-Australian plate, this one on which half of our own country is lying, and then India, and then Australia, Eurasian plate at top. So there are several major plates and then smaller plates also. So you will find a detailed list of these plates in different references. So if we plot the direction with different arrows of their movement, and the length of the arrow is representing the rate of their movement. So longer the arrow, the faster it is moving. So we can see that some plates are directly colliding. So Nazca plate is moving this direction. Obviously these are the results of sophisticated GPS readings, because the rate is very less. So we keep on observing for years and then identify that this piece of land is moving in that direction with this much rate. So Nazca plate is directly in collision with the South American plate. So this is actually the subduction zone or the convergence plate boundary between them. Our case, this is Indo-Australian plate moving in this direction approximately, and then we have the Eurasian plate. So this head-on collision directly is resulting in the formation of Himalayan orogenic belt, right, which is starting from far east up to Nepal, then some part of India, finally in Kashmir, Pakistan. So then we have almost a transform plate boundary which is sliding past. Obviously this is a very simplified figure. If we zoom into a particular area, we have more clear picture of what actually is happening there. But this gives an overall idea, right, which plate is moving in which direction and with what rate, right. So here just check this part. Two plates are moving away from each other, African plate and South American plate. So this is an oceanic ridge or divergent plate boundary, also sometimes called as oceanic ridge, right. So the rate of these plate movements can be from 1 to 10 centimeters per year. This is our case. You can see that this is the plate movement, 2.9 centimeter per year in this direction, then 10 to 20 millimeter, which means 1 to 2 centimeter per year. Then this is again the movement direction. So towards the north we have the north collision boundary NCB, which is a head-on collision, direct, a collision which is happening with the Eurasian plate. So Eurasian plate and Indian or Indo-Australian plate have a direct collision towards the north, but towards the south we have a transform boundary because the movement direction are almost opposite and they are sometimes in the slide past direction. We have west collision boundary also, WCB, but we also have a very complex seismotectonic feature. Depending upon the shape of that crack, some piece of that can be transformed, some part of that can be thrust head on, right. So depending upon the shape of that or structure of that crack or plate boundary. We have a Macron subduction zone at the south, where the Arabian plate is subducting under the Eurasian plate. Arabian plate is weak, Eurasian plate is strong. So Arabian plate is just sinking down in the mantle at this this yellow color line, which is called Macron subduction zone. This phenomena itself is called subduction, the sinking of one plate, weaker plate in the mantle. We know this because the mantle is now full of the dead bodies of old crust. So which means that this process is continuous from millions of years, that at these locations, at a particular subduction zone, the crust is now just going down and sinking, dissolving into the mantle, right. We have Sumatra subduction zone, Cascadia subduction zone. In our case, we have Macron subduction zone here, right. So there are different subduction zones in around the world. So a more clear picture, but almost the same idea. The epicenter of Kashmir 2005 earthquake was close to the North Korean boundary, right. Along the main plate boundary, there can be several cracks or fractures in the land, which can be faults. Fault is a general word. It can be referred to any crack in the surface, right. So sometimes we call different segments of the plate boundary different cracks, different faults, right. So we can call this as one fault, this as one fault, this as one fault, but obviously this is all part of the main plate boundary. But there can be several cracks which are following the movement of that main plate boundary. So you can see these lines, they are actually referring to different faults. We have Chaman fault like this, and several of the transform faults in this Balochistan region, right. So along the main plate boundary, we have also other fractures in the land, right. So fault is a general word which can be used for any fracture, and it can also be used for a segment of main plate boundary, right. For example, we say MBT in Islamabad, main boundary thrust, right. So it is one seismic source which mostly governs the seismicity of Islamabad and its surroundings, right. So its main boundary thrust, its name indicates that it is part of the main convergent plate boundary, a thrust fault. So if we look at the historical data in last 100 years and plot the epicenters of all earthquakes, major earthquakes occurred in that duration, the pattern will exactly follow the plate boundaries, which means most of the earthquakes occur at plate boundaries. It has been estimated that around 90% of the total earthquakes occur at the convergent plate boundaries, right. So you can see the situation here. Since we are lying on a plate boundary, actually the boundary between three plates, so several of the major earthquakes have occurred in last 100 years. But there are some other countries also which also have a very high seismic hazard. So you can see here this region, Philippines, then this whole Pacific ring of fire, and then this region, South American region also have a very high seismic hazard. Here in California and related regions, west coast also have a very high seismic hazard. So all of that details I have already explained. These kind of maps which show the fault lines, plate boundaries, the types of faults, their mechanism, they are called tectonic maps, right. So this is an example of tectonic map of Southeast Asia, which shows the major plate boundary, and then these triangles show that it is a convergent boundary, and then different faults also in that whole area. So the thinner lines are actually the strike slip faults, right. So this kind of map is called tectonic map. This is the phenomena called volcanism. For example, you have a subduction zone This is a real case, Sumatra subduction zone, by the way, where the Indian Ocean, where the Indian plate is subducting under this plate. The plate which is subducting is there is an ocean on that, right, and the plate under which that second plate is subducting is having a solid land on it, right. So we call this plate, sometimes for explanation we call it as oceanic plate, and this is the continental plate, right. So there at the Sumatra subduction zone, an oceanic plate is subducting under the continental plate, right. So the plate movement is following this arrow, right. So all the red dots are the major earthquakes which have occurred in that region. Some are their focus is showing, actually they are not epicenters, there is hypocenters or focus. Some originated directly at the interface near the surface. Some are very deep earthquakes like this one or this one or this one. So when one plate is subducting under another plate, it can stuck due to the forces of friction, and it can start storing energy, and one day that energy is released and that subduction again starts, right. So if we want to predict an earthquake from a subduction zone, we need to understand the whole geometry and structure of that whole subduction plane, which is very difficult to actually understand, right. So right at the start of that interface between subducting plate and the oceanic plate and the continental plate, we have several of the earthquakes, but that process of stucking can occur anywhere along the length of that movement, right. Sometime the plate can stuck at the bottom and then release, resulting in earthquake. Sometime it can stuck at the top, close to the top, right. So if we see the seismogenic depths of historical earthquakes in a subduction zone, we will find a pattern, and that will be actually following that subduction plane, right. Now one phenomena, volcanism, which I will end this discussion on, is that when the oceanic plate goes down in the mantle, it has all the organic materials and water with it, right, and it becomes steam here. So the main material of that oceanic plate, it melts, right, and it dissolves in the mantle, but the organic material, which is actually part of that crust now, it evaporates and it converts into different gases, right, and those gases actually erupt out, right, erupt out of the crust, and this phenomena is called volcanism, right. So this happens near the subduction zones where an oceanic plate is subducting under a continental plate, right. So oceanic plate contains water and dissolved material and organic material with it. When it goes down in mantle, the rock dissolves and whatever is left becomes gases, and those gases erupt out with explosions, and that process of eruption can cause earthquakes. Those earthquakes are called volcanic earthquakes, right.